All right. We're going to start. We're going to start the semester talking about Chapter 7, which is the law of sines and cosines. My opinion, there's one tricky concept in this chapter. The rest of it's pretty easy. So should be a good start for the semester where it shouldn't be anything too overwhelming. Some of you may remember doing this in geometry, but I know that was a long time ago for some of us. So you likely did this in honors geometry, though, already. All right. So the goal here, what we're trying to accomplish, is be able to solve triangles. When we say solve a triangle, what do we mean? Good. So when we talk about solving a triangle, we want to be able to find all the angle measures and all the side lengths, right? Now, for right triangles, this is easy. We've already done this. We can just use SOHCAHTOA. Right? So for right triangles, we've done this already. It's easy. We just do SOHCAHTOA. And, it's pretty easy. We did this briefly in a few chapters back in first semester, right? For non-right triangles, though, we can't use SOHCAHTOA. Instead, we're going to develop two tools to use called the law of sines and the law of cosines. So I'm going to abbreviate law of sines as LOS and law of cosines as LOC. Since we use those phrases pretty much or on a regular basis here all through this chapter, I'm just going to abbreviate them. Is everybody okay with LOS and LOC? Okay. All right. So we're going to start by doing a derivation to show you kind of where the law of sines comes from. When I show you a derivation like this, is this something I'd expect for you to be able to repeat on an exam? No. Is it just for you to kind of understand where the formulas come from? Yes. Okay, so don't get too bogged down in worrying about the details here. It's mostly just because it's an honors course and we want the rigor of the course to match the title. So we do things like this, although I would not expect you to be able to repeat these same kinds of steps. First things first. Here's a triangle, ABC. Is this a right triangle? No. How do you know it's not a right triangle? Doesn't have that little square in any of the corners, right? Real basic. Very important convention. You see how we've named these side or the angle, named the vertices A, B, and C. Everybody sees that? I'm going to name the side lengths lowercase a, B, and C. But it definitely, absolutely, positively really matters which side I'm going to label as A, B, and C. So the convention that we use is the side opposite the vertex is going to get the same letter name, just the lowercase version. So if we're talking about this side over here, what letter should I name that one? Little a. And then this side would be little c, and then this one then is obviously little b. Everybody's okay with that? Okay, when we write these formulas out for the law of sines and cosines, it's going to be under the assumption that we're naming our triangles in the same kind of way, where the side length opposite the angle has the same letter name, just the different lowercase or capital version. Everybody's okay with that? Very, very important. If you mess that up, the formulas are not going to work. Okay? All right. So if I want to develop a way to find the side lengths or angle measures for this triangle, what I'm going to do is I'm going to split this into two right triangles by just drawing an altitude somewhere. I'm going to label that altitude as h. Remember, an altitude from geometry is a segment that goes from the vertex of one angle or one of the vertices of a triangle to a side, and it intersects that side at a right angle. It could be if it's oblique, or if it's an obtuse triangle, you might have to extend the side to draw in the altitude, but that's basically what's going on. So now I have two right triangles, right? I have the triangle here, and then I have a right triangle here. Everybody agree with that? For the green triangle, I can say that sine A is going to equal opposite over hypotenuse. And for the blue triangle, I can say that sine C is going to equal opposite over hypotenuse. Everybody agree with that? I can use those SOHCAHTOA here because I divided this triangle into right triangles. That's why it was all of a sudden okay for me to use SOHCAHTOA. Everybody catch that? Okay. So what I'm going to do now is I notice there's a variable in common with each of these triangles, right? That variable being h. So I'm going to solve each of these two equations for h and then set them equal to each other. So in the first equation, I can cross multiply to get me, oops, that's a lowercase c. And here in the second equation, I get h equals a times sine. That's supposed to be an uppercase c there. C is probably a terrible letter to use for this when writing it down because it's hard to tell the difference between lowercase and uppercase, but you'll just have to deal with it. So what I can do now is I can set them both equal to each other. And what I'll do is divide both sides by AC. And that's going to give me sine A over A is equal to sine C over C. Everybody good with this? If I go back to the original drawing, I could draw in another altitude. That's not very altitude-y looking. Oh boy, really mucked that up. And I can call that a second H. And I repeat the same process, right? Which would give me, like, involving the angles, that one would have been what? B and C or something. But what it boils down to is this. That is our law of sines. So let's say we want to solve the triangle where angle A is 32 degrees, angle B is 73 degrees, and side C is 10 inches. The first thing that I would do is what? Well, that's a good one, but even before I do that, I would do something else. I just draw a picture to kind of give myself an idea of what's going on. But certainly, as soon as I draw that pic, you don't really need to draw, but I think it's often helpful. Just to make sure that you have things in the right location. So I'm going to call this one angle A, so that makes that side A. I'm going to call this guy angle B, so that's going to be side B over there. So that's angle C, and that's side C. Oops. And I'm just going to label that as 10 inches. All right. So, Ms. Tiller, you were saying you can find angle C straight away by doing what? Minus them from? Good. So this was called the triangle sum theorem. This was something that you learned in your geometry course. So whenever you're given two angles, it's easy to find the third one, right? It's always going to be 180 minus the other two. Everybody's okay there? Okay. So that's one of the three things that we need for our answer. We also need to find side A and side B, right? How are we going to find side A and side B? I'm going to use the law of sines. So the law of sines has two sets of equal signs in it, right? So for this problem, which two of these ratios are we going to set equal to each other? Well, let's pick a side to solve for first. What side should we solve for next? B or A? A, you say? Okay. So for solving for A, which two of these ratios are we going to use from the law of sines? Good. The ones with C and the ones with A in it. Why did you pick C and A? Very good. That's exactly right. So we chose C and A because we have everything we need to know about C. We know both the angle measure and the side length. And we want to find out about angle A. Or side A, excuse me. So I can say sine of 75 over 10 is equal to sine of 32 over A. And now I just need to solve for A. So what I like to do is I like to cross multiply. That gives me A times sine 75 equals 10 times sine 32. And then I can divide both sides by sine 75. And then it's calculator time. When I type this into my calculator, what mode should I be in? Degrees, very good. How do I know I should be in degree mode? I'm using degrees in the problem. Hey, you know what? Like, there's no harm in asking some softballs here on the first day, right? Oops. Are we debating that softballs are harder to hit than baseballs?
No, are they like softballs are bigger? Yeah.
I think what they've decided is like it's harder to hit a softball far because they're not as dense. I think is how it goes. So it's easier to hit a baseball far, but it's harder to make contact. Wait a minute. No. Yeah, that's fine. All right. So there's my value for A. Now to find B, what can I do there? Right, that's the last thing now that we need to find. How do I find B? Can I use the Pythagorean theorem? I know two of the side lengths.
No, you can't. It's not a right triangle.
Not a right triangle. You cannot use the Pythagorean theorem here. Make sure that you're being careful about that. You'd be surprised how frequently students are like, oh yeah, and I'll just use the Pythagorean theorem. It's like, you know, right triangle, what are you doing? All right. So, can't use the Pythagorean theorem. What can we use? Law of sines. We don't know the law of cosines yet. I wouldn't use that. All right. So which of the two ratios are we going to use? B. You could use A. I'm going to use C. That'll give me a slightly more accurate answer. Why would that be slightly more accurate than A? A has rounding in it. Very good. Everybody happy here? Okay. I don't do this. Okay. I lied. All right. Here is the tricky situation. Yeah. So there is a situation when using the law of sines, when you're given one angle and two side lengths, where weird things can happen. What are those weird things that can happen? You can have no solution, one solution, or two solutions. All right, so the ambiguous case, the place where we have to be concerned about, is when we have one angle given and then two non-included sides. What do we mean by the non-included sides? So if this is my angle A, that means we would have those two sides or these two sides, but you would not have those two sides. Those are the two sides that make up angle A. Okay? So if A is the angle that's given, when we say non-included sides, it's either the two red ones or the two blue ones, but you can't have one red one and one blue one. Tying this back to geometry, if you guys remember your triangle congruence theorems, yes? Okay. So what were those triangle congruence theorems? Give me an example of one. There are three letters. So side, 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 yup. Side, angle, side, which, hold on, side, angle, side would be if I had the one angle and the two included sides, right? Okay, you said angle, angle, side, good. What? You said angle, angle, side. That's it, right? Oh, angle, side, angle, yes. Thank you. What is there not? There is no side, side, angle. Why not? Because the two triangles are not guaranteed to be congruent, because you could have two distinctly different triangles that have that same congruence. That's what's going on in this ambiguous case. So remember back from geometry, and kind of connecting that idea back here is often helpful. Okay. All right. So BC is a segment, right? It's the side of the triangle. So if I look at the picture, side BC is also called what? The hypotenuse, right? So all this is saying is if the hypotenuse isn't the longest side, no triangle is possible. But the obtuse angle situation is an easy one. So if the given angle is obtuse, all you have to do is check to make sure the hypotenuse is the longest side. And then you just go about doing the law of sines as given. You don't have to worry about any other situation other than that. Is everybody okay with that idea? So case 2, if the triangle is or if the given angle is a right angle, it's the same situation as case 1. You just have to make sure the hypotenuse is the longest side. And you just only get one triangle. In fact, we could change, my bullet points there to be greater than or equal to 90, and it's fine. So the last situation here is the one that we really have to be cautious about, as many things can kind of happen here. Okay. So, what is this saying? It's saying that if you have an acute angle and the side opposite that acute angle is smaller than the other given side, that's when the weird things can happen. Okay, that's the only time where weird things happen. Right? You can have impossible things happen in other cases, but they're usually easy to recognize. That, like, the hypotenuse isn't the longest side. That's bad. But here, you don't know that the side opposite your acute angle is the hypotenuse or not. So it could be small, it could be big than the other side. That doesn't really change anything. So let's look at a couple of examples here where we're just trying to work out how many triangles are possible. So first thing that I'm going to observe is that I notice that P is an acute angle. Everybody agree with that? And that the side opposite P is smaller than the other given side. This is the ambiguous case. So we're going to try to determine whether we can have 1 or 0, 1, or 2 triangles here. The easiest way to do that is to just try to set up a law of sines and see what happens. So using the law of sines, I can say sine of 56 over 16 is equal to sine of q over 19. So I'm going to cross multiply here. And then divide by 16. Everybody's okay here? Okay, so I'm going to go and type this into my calculator. When I do that, I get about 9.8 or 0.984. And this value here is going to tell me what's going on. So if this value is less than 1, I get 2 triangles. Is if this value is equal to 1, I have 1 triangle. And if this value is greater than 1, I have 0 triangles. So in our situation here, we have 2 triangles. Let me justify to you a little bit more because this seems a little arbitrary, what I just wrote down as to why that would imply that. So if I went on continuing to solve this, to solve for angle Q, I would take the sine inverse of both sides, right? Now, where is sine positive? It's positive in the first quadrant and also in the second quadrant, right? That's why you're getting 2 possible triangles there, because that angle Q could have 2 possible answers to it. Now, if sine inverse was just equal to 1, that happens just one place in the first 2 quadrants at 90 degrees. Basically, if sine is 1, you're dealing with a right triangle. That's it. Everybody agree with that? Hello?
When you said sine is equal to 0, do you mean 1 equal to 1, or is it equal to 0? Like,
So sine,
0.984.
oh, yes, thank you. That should be a 1. Very good. Thank you. And then if I get a value bigger than 0, or I'm sorry, bigger than 1, are there any values on the unit circle bigger than 1 for sine and cosine? No, that's an impossible value, so that's why you're getting no triangle there. You're just getting a situation that's nonsense. Does that help kind of connect it back to what we were doing first semester to justify why we're getting, 1, 2, or 0 solutions there based on that? So I can't tell just by looking at the 3 numbers what situation I'm going to be in. I'm just going to start the solving process. And when I solve for that first angle, that's going to be what tells me what's going on there. Okay? So if this number here is less than 1, I get 2 triangles. I'm going to get 2 answers for that angle. If that answer is equal to exactly 1, I'm going to get 1 triangle. It's a right triangle. And I could actually do like Pythagorean theorem and SOHCAHTOA and all that kind of stuff on it, since now I know it's a right triangle. And if that number is bigger than 1, I'm done. There's no triangle possible with those measurements. Is everybody okay with that idea? So let's look at an example where we have to do this in practice. Okay. So first thing I'm going to do is I'm going to analyze the information that's given to me. So I'm given an acute angle, right? And the side opposite the given angle is smaller than the other side. So this is the ambiguous case. I'm going to either have 0, 1, or 2 triangles possible here. All right. Well, just like we did before, I'm going to set up my law of sines. So I'm going to solve for side. I don't know why I wrote a little a there. I should have wrote 12. I'm going to solve for angle A by cross multiplying. And then I'll divide by 10. So let's check what that value is real quick here on our calculator. I get something that's less than 1, so what should I expect here? I have 2 triangles then possible. Okay. So let's find the values for those. So next thing I'm going to do is take the sine inverse of both sides to find the value for angle A. When I do that, I get 63.1. Now let's go. I'm gonna save 3 decimal places. Sometimes this gets a little finicky. But remember, this can have two answers, right? Angle A could be here, or angle A could be over there. Everybody remember that? So my other answer would be 180 minus 63.097. Because remember, the size of this angle with respect to the x-axis is the same. Right? That was an important tool we used first semester. So 116,903. So at this point, I'm going to reorganize my work here a little bit. Well, that's not right. These were, what were letters did I use here? B, thank you. Goofing this up. And then A is this other one, right? That's what we just found. Everybody's okay with how I'm formatting here? Just to kind of keeping things organized. Now that we have two answers going on. So let's find angle C over on triangle 1. So I can just do 180 minus the other ones. Everybody's okay there? So that's 68.903. And if I want to do angle C in the other triangle, same idea. So 15.097. Everybody happy so far? The last thing I need to do is find side C. So to do that, I'm going to use the law of sines. So I'm going to use sine B over B. I chose to use B instead of A because there's no rounding in B. And then I'll have sine of 68.903 over C. Now, I can't avoid having to use a rounded answer there, but it's the best I can do. So when I cross multiply and divide, I'm going to stop showing the cross multiplication step here because I'm just kind of sick of doing it. So here I get about 12.554. And if I do the same thing in triangle 2, but use my angle A from triangle, or my angle C from triangle 2, there. and I'm done. I'm going to post some problems for you guys to try. And then we'll pick up working on this some more tomorrow. But I'm done here for today. I think that's plenty.